Produce.
Hey, David. How are you?
Pretty good. How are you?
Very good. Thank you. Hey, Vikas.
Yes. Hi, David.
Just give everyone maybe a minute. I got a note from Bala that he is still working. He has worked on something that he wants to review next time. He has a conflict today. So I don't have any specific agenda items for today. Let's see if how many people join. Then we can talk. Otherwise, we may have a very, very short meeting.
Actually, if there is no agenda, I would like to ask you something.
Yes, go ahead. Sure.
Yeah, it might have been discussed way before, but I wanted to know about the ESD guidelines on the interconnects, like bonding interconnects. Are there any, or how we are like, if you have any idea about it, how we are taking care of it?
Good question. And let me give
I
you a
have
moment.
some idea. So, are you talking about the hybrid bond or which level of
Yeah.
interconnect?
So hybrid bond, or if we have interposer, any one of them. Like in our 3D stack, how exactly we are going to address this?
So currently the industry has, even for hybrid bond, not adopted 0 CDM ESD spec. They are still constraining and designing for 5-volt CDM. ESD.
Okay, so let me write it down.
For the hybrid bond. Now,
okay,
for microbump, it could be higher. As the package substrate size associated with it, the capacitance overall package goes up, it'll be higher. So there is a, I think IEEE JEDEC, IEEE ESD standard for 3D, but nobody is looking at 0 volt currently, if that's where you were headed. Yeah, and of course there is no human body model for internal interfaces.
Yeah. So there is no. So what is the document, Pratyush, again?
I'll have to do Google search to find the ESD 3D spec, but let me do that offline and put it in chat if I find it.
Yeah, there's so there's actually, yeah, as far as specification, where to put that data, I should share my screen. This is the going back to the this is this white paper that we did way back when.
Yeah, I've seen. I've seen this one. Yes, I know where it is.
Yeah, and I know we had ESD in that, and here's what it says, right? That the electrical properties, there's JET30 E100, includes electrical and functional properties, and then there is the ZEF, which became CDX-ML, that also has per pin ESD ratings. And then
David, what was the last thing you said there about what type of ratings? I was trying to connect.
ESD ratings in JET30.
Oh yeah. That's in section E.
Yes,
JET30-E.
exactly.
Yeah. Okay.
Yes, exactly. That's exactly what I was sharing with Vikas.
Okay.
I think
Yeah.
you have some IEEE paths there down below for the ESD specification relating to these, what the standards body has currently, right? But what E100 is basically your means to specify the ESD rating of the IO, right?
Yes.
Yeah,
Yes.
but we also need to think about how much ESD. I mean, because probably you're going there.
Yes, that was the next step. But first, like,
Yeah.
you got it. Yes.
Yeah, so I have spoken to many people in different summits on this topic in the past, and including, people selling the ionizers to the foundries and stuff. And my takeaway has been that with the usage of ionizers, when you are doing the wafer on wafer, when you do the wafer to wafer hybrid bond, that's enough to actually consider 0 volt CDM ESD less environment essentially for the bonding process.
Yeah. Okay. That's for hybrid bond.
Okay, can I clarify something here? Patrush, did you say that the ESD ratings are only applicable to the terminal? It's applicable to the entirety of the device. I'm checking to see if it's also applicable to the terminal. Is that what you meant?
Yeah,
It
it should
is
be
applicable
per
to the
terminal,
terminal.
technically.
Say again.
It should be per terminal.
It should be per terminal. Okay, let me check that. Okay, I'll come back to you on that. It'll take me a few minutes to figure that one out.
Okay. And for interposer, Pratyush, anything when we have interposer?
Yeah, there is a different spec. I'm trying to find that online,
Okay.
and then
Oh.
we can carry on the conversation. If I find something, I can share that.
Yeah.
Okay. And then the micro bumps will have. So why are micro bumps not treated as hybrid bond itself? In a way, like that is also contained. So it should be like there shouldn't be any human interaction anyways. That human body.
Yeah, it depends on where, right? It depends on where the bumps go, right?
Okay.
In hybrid bonding, the environment is such that what Pratyush was saying is that the environment is such is that you don't expect any charging of the device. So when you put
Like
the
ionizers.
wafer, right? Now, once you go to interposers and things like that, there's basically two sides to this. One is some of the micro bumps are going to go out on the bottom of the interposer, right, and go to the outside world.
Correct.
That outside world will have the ESD requirements, right? It may be charged and so on. Then you have the die to die. Which people are saying, okay, right? You are not going to have a human body model, right? But you will have a you may
Charge
have,
device model.
yes, right.
CDM.
You may have CDM because you are assembling in the assembly environment. You may have charging of the device.
Oh, okay. Yeah, you are right. And they don't have that ionizers to take care of it.
Right.
Okay. In hybrid bond, we have ionizers. So an environment, like you said, basically the environment.
Yeah.
Okay.
And even after hybrid bonding, the bottommost die must have a proper ESD protection. If for some reason there is a TSV that goes from the bottom die to the top die directly, then that pin on the top die will still need to have the proper ESD protection, right? Whatever goes to the outside world can be traced to the outside world.
Correct.
It needs to have its ESD protection.
Okay.
At the appropriate level.
Got it. And
All
what
right,
is this?
I am after making a confirmation here now. The mapping of the ESD in the JEP30 is currently at the entirety of the package. It is not at the individual pin. making it at the individual pin requires a small modification. It's very small, and I can put that in for the next release.
Yeah. So Michael, when we did the translation CDXML into JEP30, CDXML actually did have it per pin. So that was, I guess that was lost in the translation.
I guess it was, yeah.
Yeah.
All right, so I have it in there now.
Okay, so I mentioned before other folks joined. I got a note from Bala that he's has some proposal that he's working on, and he can share that next time. But he has a conflict for today, so cannot make it. I don't have any other items on the agenda. Any other questions from anyone? Any thoughts?
Yeah. One last question on this ESD only. What is machine model? I know human body charge device. What is this machine model?
That's when the assembly machines are charged, right, for whatever
Oh,
reason.
okay. Got it.
So basically, so the way it works is there's actually, I think it's a JEDEC standard that defines each of these models.
Yeah.
At what voltage level and right, what currents and so on, how much charge each of these models needs to consider.
Got it.
And some of them are pretty big. I know we had a hard time meeting some of those. They were like 1,000 volts or something like that.
Yes, I've
So I
heard
was
that.
not able to find in Google. It's JEDEC, it's not IEEE. Yes.
Right. Yeah, it's JEDEC thing.
Yeah, reliability or these kind of things are almost always JEDEC.
Yeah. I guess in my head, JEDEC deals with the physical goods, and IEEE deals with the virtual goods, like formats, specifications, things like that, right? If you need to describe a physical good, probably especially a chip or some kind of electronic device, JEDEC is going to be the place.
Hmm.
Well, JEDEC also does all the electrical definition for the interfaces for anything to do with memory. That's not physical.
Well, it's a description still of the physical good, right? What I mean by virtual goods that IEEE does is like file formats, right? Verilog, UPF.
Oh,
You know,
right. Okay.
You know, even Microsoft Doc is actually IEEE standard.
Okay.
You know,
right.
C++ maybe IEEE. It goes through. You know, so some of the languages go through IEEE, things like that, right? It's much wider than the electronics itself, right? I know I oversimplified it, but you know, that's my zero order simplification.
Mm.
Yeah. Okay, so I think we can conclude for today. John, I had a meeting with John and Mohammed. So we had a very good discussion. So next week we are going to talk about SIPI. John, if you need to sync up before that, do let me know. And then Bala is going to go 2 weeks from now, talk about tests. I did have a chance to review 3D blocks. I find it very basic. Right.
Yeah.
So there isn't much meat in that, right? It's kind of standard description that anyway, I think CDXML and JEP30 are way larger than this and way more useful.
Yeah.
Just my 2 cents on that.
Yeah, I also have similar, like when I was going through all the documents, I found like it's very basic. The good thing is they go into details. One thing that I really liked about it is, which is also in JEP, like how they defined the connections. Like every bonding, they made it a connection, like an object, and under it you can define lot of things. So I think that structure was good.
Yeah. Yeah. I need to take a look at that part.
Yeah, see the
Second
connection,
time.
their
Yeah,
object, how actually they do. That was, in my opinion, that was pretty good. Like you can define every connections completely like as its own entity with its own attributes. Other than that, obviously, JEP is much more comprehensive. It has like materials and all that. They have nothing about it. Nothing.
Right. Yeah. Yeah. To be honest, I'm going to take a second look at the connection, but here's where my confusion comes from. Right. Number one, in terms of logical connectivity, you get that from Verilog. In my mind, that is the golden representation, right? Because you're going to take that net list and run it through verification or whatever you do. That's your golden verification. That's the golden net list, and that gives you the logical connectivity. As far as physical connectivity, that's in a way straightforward too, right? That's a geometrical problem that says, okay, when you place these two things on top of each other, do they connect or they don't, right? And there's a little bit of definition about what does a good connection mean. But
and
other than
actually, just like there is one thing that it says in early chip design feasibility study. That's where if you put all that information, initially it can actually do like, okay, this is even possible or not possible if you want to. Like align bit, if you put it with alignment marks and all that.
Okay. Maybe. Yeah, let me take a second look at this.
Yeah. Like I like the some of the things like structure, like they have created an object just put it all together with proper alignment marks. If you have like proper alignment marks aligned, then it can quickly do initial a feasibility study itself. That kind of stuff. Yeah.
Yeah. So you're talking about you have ready dies and do a feasibility study of
Correct.
Right. But here's the dirty secret about that, right? I understand how TSMC thinks about dies are ready, right? And can they align? But these dies do not magically appear, right? There's a whole lot happening before that to make them align, actually, right? And to see if it's feasible, right? In many cases, you wouldn't have the die ready, right? So when I'm doing the initial feasibility study, even if I get a third-party die, and I'm developing my own die that I want to put, and I want to get that, I want to put the third-party die on top of mine, I don't have my die defined, right? So I'm going to have to go and define it and then figure out if physically they align. And the thing is, when I do that, I will make them physically align. It's a matter of doing it rather than checking if it's feasible or not. So in the context of manufacturing, definitely I see how that is valuable to a manufacturer, right? To make sure that they don't get dies that are totally crap, right? Because I'm sure that has happened too.
Like think from like we are OSAT kind of thing, from OSAT perspective, who has no control on the design. For us, it becomes like relevant. See, I see your point. Yes. Like you said, you can do it. Yeah.
Right. But by the time it gets to you, you really have no way of telling
Yeah.
whether these align or not, right? It's better,
Yeah.
the guy who generated these dies needs to make sure they do align and to tell you how
Correct.
to align them.
Yes, yes. And here we just check. So it's a
Right.
good like check kind of a thing. Let's put
Right.
it this way. Yeah.
So in that context, I don't know what value it would be to you if I provide you the full connectivity and they align, right? And if they don't align, what I should have been able to catch it on my end.
So think about this scenario, David. Like, so here is what we are thinking. Like, okay, we get bare die from two different vendors, suppose. Now we have capability after like their IOs to put bump on it. Like we also can put like 2 layers on it and then do it.
Okay.
That kind of scenario I was thinking about. It's a possible scenario for us.
Yes,
So very viable.
yeah. In that context, I can see that. Yes. Yeah, kind of a way to translate my intent, how I thought the dice need to align to you, so that you can tell me, can you align them that way?
Yeah, exactly. Yes.
Okay. Yeah, that's an interesting approach. Yeah, okay. I think with the current scheme in JEP30, that should be translatable too, right?
Yes.
Because what Michael is working on is to get the stack information, and once the stack information includes XYZ coordinates of all the pins, that in a way gives you the connectivity, right? You can immediately tell what's connected to what, and you can examine it.
Yeah.
That's what I'm thinking. Yeah. Okay.
So, David, I had a question on test.
Yes.
So
Okay.
yesterday we were in an internal call, and the first question that comes, right, when we talk about open chiplet economy and when we are buying off-the-shelf chiplets, and I'm sure this conversation would have happened in the past, in terms of collateral. So basically, any chiplet vendor, in terms of selling a die, if they're selling IP as a chiplet, then they are probably giving us all design collaterals, right? The necessary collaterals, including everything relating to test. So if they are, let's say, selling wafer or diced die, even for assembly, let's say, most likely they'll sell wafers, right, to us.
Right.
Then they with a known good die map, let's say, what is the assumption we need to make here? There will be a full suite of tests run, full ATPG run on these externally sourced chiplets by the assembler, right? Assumption
Right.
A. Okay.
Yeah, so that's a very good question, and there's a little bit of gray area, right? Because you get a non-good die. The question is this, right? Especially with the die-to-die interfaces, right? Do you need to run a full link test on both sides?
Why did you just say link test?
I mean, between basically
Yes,
send data from one die to the other die, right? You send the data from one die and you capture it in the other die, and then you compare it to verify that your assembly worked.
Okay, so you're just talking about the interface test that you do.
Okay,
But
so in that case, whoever gave you the chiplet with the die to die needs to give you an information about how to capture that data and how to extract it out, right? Whether it's a pattern or right something, right? Some documentation, whatever, so that the final test of the integrated chiplet system can exercise both.
right. So yeah, sure. So we definitely need to have a standardized way to load the vectors for these internal tests, these link tests in a multi-die. But I'm going one step beyond. I'm asking, because typically in my experience, everything all the vectors you run during a wafer sort, you rerun all and maybe some more parametric tests when you do the post package assembly, right? We call them full test.
Yes.
So we are doing all the internal guts of the second die also tested in this. So that's where I'm like, everything needs to be exposed, right? In that case. So the challenge there is companies have different way. Basically, it has to be EDA agnostic, essentially. So
Yeah.
what defines a very basic pattern that is the language of all current, let's say, ATPG and test analyzer tools, basically, right?
Yes.
In ATPG or that language. Michael, you would know better here than us.
I'm trying to understand what type of test are you referring to?
We are talking about the full test. You'll run the full
full suite. You want
full
so
suite.
once
I'm talking
actually, yeah. I
scan test,
think let me try
BIST
to
test,
explain it.
internal BIST, die to die
So,
link test,
Okay,
everything.
two of you talking together, and I can't understand what either one is saying.
sorry, I'll mute.
Sorry, so I'm saying full test. Basically, you have internal scan tests for the die. You have BIST tests for logic, for memory. Then you have these additional tests for the loop back tests for the die to die interface here. Everything.
Right. Okay. So where did the rules come from?
Yeah, that stack. I don't think anybody here understands. Like when we talk about say just a scan test, right?
Yeah, that's what I think. That's what Bella's feedback was, that every EDA vendor does its test a little bit different, and they're not fully may not be fully compatible, or they're not fully translatable, right? So what he was saying is, if you have a die that's done with Synopsys test and a die that's done with Siemens test, testing both becomes a crazy exercise, right? Making sure both connect, right? So you basically have to work with both tool sets to kind of combine them together into one final test. So yeah, that's so there's two sides to this, the way I'm thinking about. Okay, usually there's actually three sides. One is in terms of standards for testing. How do you test stuff? That's IEEE, right? I think they have a pretty good track record and collaboration on defining those things. Right. Then comes the EDA specific stuff, right? How do you encrypt stuff? How do you what is the word? How do you obfuscate things? How do you exactly what the physical connectivity looks like? I think that's EDA specific stuff, right? And the third one is, okay, what is the common information that needs to be is there a common set of information that can be carried for a chiplet that describes what the test is, such that a tool or a user would have easier time integrating the chiplets together, right? So I think the way we are going and the way we are thinking is OCP can help with the last part, right? If there's a common set of information or some kind of a set of information that can be carried around for users to simplify their life, we can do that, and we can define that.
Wasn't that supposed to be part of the test design kit?
Yeah, this will be part of the test design kit, basically.
Exactly.
And there has to be first be a reference language developed for this, because we are talking about let's start with the first layer you said, right? The EDA agnostic layer, fundamental layer. So you have a circuit. You have a circuit. You have a set of input pattern, and you have a set of output pattern, right? These are pure Roberts we are talking. And then each EDA tool with a map of that circuit and the comparison of the input versus output gives you a test coverage and the fault location isolation also, right? That's really interpreted by the EDA tool. So the question, so tester, when we are doing the ATE test, it would have those things loaded in. So there must be a common language today existing, right? Because people are using, let's say, common Teradyne tester, but the underlying DFT is either from Synopsys or from Cadence or from Siemens, right? So I'm
Yeah.
pretty sure.
So
Yeah.
if your question is what is the reference language, that's actually I believe it's machine dependent, right? Depending on the capability of the machine and the prop, right? You would define your prop card, what you're probing, how you're probing it, and then define write it in for that on that machine specific language and let's say API, you know, and capabilities to exercise that. So yeah, there is definitely an next level translation. But again, right, it's easy when you have the issue is not that last part, right, where it gets translated to a the actual tester, right? What bits need to be read out and so on. I think that is open, and every EDA vendor, right, probably supports those, and whatever pattern they can think of, they can translate it into that machine's language, right? But the issue is not in the chiplet itself, right? How do you do the test? The issue is how do you get two random chiplets and make one test?
Oh, that's a yeah. So you are you talking about basically in tandem test, not so you're testing chiplets simultaneously, multiple chiplets, right? So you need to have a DFT and test strategy for multiple dies. So that goes into the design phase itself.
That's right. Basically, right, when you're putting all these chiplets together, what does that mean from testing point of view? How do you do the test, right? And that's the piece that I understand is where the struggle is.
And what this is no different than taking multiple printed circuit boards, putting it into a system, and then testing the system.
It's very different, Michael.
So okay, what's the difference?
So each EDA vendor will have their own a little protocol and language to describe the test of each chiplet, and it may be implemented a little bit different, right? Even the number of pins, some are some may have, think of it this way, right? Some may have 2-bit parallel interface for testing, some may have 4-bit parallel interface for testing, right? So now when you get to the substrate level, how do you combine these two together, right? There has to be somewhere a translation from one to the other and so on, right? So
Isn't that similar to using a combination of JTAG and BIST? Right, so in one piece of circuitry, you have one method of performing a test, and you have access to that via a series of test pins. In another piece of circuitry, you have a different method of testing that was applied, and maybe some test pins accessible to it. Now I bring the two of them together. Both of those individual pieces have been tested independently, but now I want to test them as an assembly of those two circuits.
Not only as an assembly, but we need to test them as one monolithic piece, right? You send, right, when you have a die-to-die interface, you send the data from one of the die into the other die, and then you extract the data from the other die. If the interfaces on both dies are implemented slightly different, you may not be able to do that, right? Or you may be able to do that, but through quite a bit of hoops, right? So
okay, but aren't we pushing for the standard definition of the interface on one side to the standard definition of the interface on the other side? Now, if the second interface has a different configuration, so long as it still complies with the standard, the system should be able to recognize that I have configuration A of a HBM interface to a configuration B of a HBM interface. I should be able to understand that in order to be able to recognize sending data from version A to version B.
So Michael, let me make it easier in a way, the challenge, right? So in your case, when you're doing the PCB test, both the PCBs are in-house design. You control the whole environment, everything, right? Versus if you buy a PCB from outside, do you run everything, or you just run a boundary scan connectivity check probably to ensure, because it comes as a known good PCB to you, right?
Right. Yeah. Because so that's the key. It comes as a known good PCB. Therefore, when I put that external PCB together with my internal PCB, I'm now testing the system as a unity. I'm not trying to, within that system level test, perform specific tests for the external board and specific tests for the other board. I'm doing it at a system level, and I need to know the protocols of how does one board communicate with the other board, and when I do communicate in this way, what is the expected response from the external board?
So, Michael, that's not entirely true, right? So, here's where I think the difference is. So, the supplier who is giving you the PCB, the so-called non-good PCB, they in their factory they perform the test and they said this is a non-good PCB, right?
Yeah.
And they put it on a box, put it in a box. They put it in a container, put it on a ship, load it on the ship. The ship traveled 10,000 miles, got unloaded on the dock, and then that box came to your factory. Somebody opened it, picked up the board, and plugged it into the system. Is that a non-good board? Right? If I'm manufacturing the boxes, I would like to verify on my end before I begin the next step of assembly that this board truly still works, right?
All right.
Right?
Okay, but that is no different than if whether I'm creating an advanced package versus creating a system level assembly in a different country. And we did this all the time. The question arises is that is the assembler going to have the capacity to perform a full-blown test on the individual component that goes into the assembly prior to doing that integration? Because if he doesn't have that capacity, and most of them time they will not have that capacity, it's very, very rare that they will have that capacity. Then how is he going to? He has to take it at face value that I can perform some level of test, but it will not be the same as the test that the manufacturer for that component has created. The same thing.
Yeah. So I see. Well, as we come closer to silicon, things are very different, right? So I'll give you a monolithic example from past. Single die in a package. When we run the full test, the yield fallout is more than upwards of 5%, right? So I'm talking about doing the full test within the die now only, and because of the environmental change as well as whatever the package does to the design, right? The original. There could be up to upwards of 2 to 5% yield loss at that stage.
Yeah.
Right. So that's unaffordable. We talk about DPPM numbers that just cannot. So we have to run full tests no matter what, right? Basically for the silicon when we are assembling the silicon in the package.
Yes.
Yeah.
No, so let me just clarify that. I do not believe that when they put the die into the package that they run 100% of all the tests that they had previously run on the die. I think that there are certain functionalities maybe a subset, maybe 70% of the tests that they run on the die, they will rerun after the die is inserted into the package to make sure that the assembly into the package does not break any of the critical functionality of the die. So, for example, doing read-write cycles on a die, right? Typically, you have a maximum limitation before the die will die. When I put the die into the package, I ain't going to be testing it to the life of the die. I'm going to be just testing it to see if I can perform read-write cycles to the die. Once I'm able to confirm that, I now know that the connectivity between the die and the package is good. So that type of test is what we consider system-level tests. It is tailored specifically to the operation of assembling the die into a package.
I think, Michael, I think that the question is the other way around, right? You're right. There are cases where you are not going to do all the tests, right? And that again, and what that depends on is what kind of application it goes into, right? And who is the customer? What are they doing, right? That customer can kind of tell which test is sufficient as which is not, right? Which is not necessary, right? You definitely cannot run everything at in some cases at a at speed full system test in a package part, because if it's 1,000-watt parts, you just cannot do everything, right? So you have to be judicial about what you're testing and how you're testing it. However, right, I think the question is on the opposite side, right? There's enough examples where you do want to test everything possible at the end on the assembled part, right? Think about, probably the easy example is medical devices, right? If you assemble chiplets in a medical device, you as a recipient of that medical device would prefer to have that to have been fully tested 100%, right? No failure, right? The rules are like that, and probably the same thing applies to automotive. In some of these cases, not only after the assembly, you want to test the full part, but you want to test it every time you boot up. You want to be able to perform a test and make sure the device still works, right? For a car, for example, self-driving car, you probably want to be able to perform some level of testing once you power up the car before it starts going, right? Because once it starts going, it's too late to find defects, right?
Yeah, but again,
I'll make it even easier. I'll give you the example of hybrid bond. You won't be able to test, maybe sacrificial pair is too expensive, so you're only testing it post bonding.
Yeah.
Right. Okay.
So,
I think the difference is what we're saying. I think we're saying the same thing, but I think the difference is the when you say 100%, there's no such thing as 100%, right? So
Sure.
I'm taking when you say that literally. So if I had 100 tests done at the die level, when I integrated it into the package, I might actually have 110, or I might have 70. It depends, but for sure, there will be some unique rule tests that are not able to be performed at the individual level. And for sure, there are some that would be overlap with what you have done. So
yeah, so Michael, I think what we are talking about is, I think it's slightly different. It's not the example comes to mind that is to explain a little. It's not what the test is and how many tests you want to run, and it's actually in the nitty-gritty details of how do you interface with those tests for two different chiplets, right? All the nuts and bolts are mismatched, and the way to think about it is, right, you have Windows and you have Linux. And if you open browser on both and you browse anything, it looks the same, right? But underneath, all the APIs and libraries, all of that is different. So you wouldn't be able to run a Linux browser on Windows, right? The APIs are different. And that's where the testing is right now. People, right, you have the testing chiplets. What chiplets do is like provide a binaries that are supposedly able to run on any platform, but then testing APIs are different, right? So you cannot quite run it together. And if you have somebody who is dedicated and can go and dig through all the details and the tools and options, and would be able to combine probably the two chiplets together and test them at the same time, right? Figure out what the API is for one, what the API is for the other one, what options need to provide from one tool to the other tool to make sure they kind of right. That's where the difficulty is.
Right. Okay. I see. So sounds like we need to have another standards group work on that.
Yeah. So what Bala was looking to do is right, and what we are trying to do with the test design kit is provide that layer of description that says, hey, this is how this test was done, this is how that test was done, these were the options, and this is how you would translate from one tool to the other tool. So that whoever is integrating it doesn't have to go and bang his head against the wall and try to figure it all out, right? We simplify at least some of the data exchange, right?
And is that what you plan to do through the test design kit?
Yes.
Okay. I think, yeah.
Right. Yeah. And our first baby step for that was, okay, let's identify at least the test pins and the test modes, just so we know what they are, right? First level zero order simplification, right? Let's identify that pins which are used for test, what they are, right? Which are clock, which are data, and then we knew that this is a little bit incomplete, but we depend on Bala to. Right now, we depend on Bala to tell us what is the next level that we need to do, right? Protocols, description, and so on.
Okay. All right. Yeah.
Right. We'll leave to IEEE to still be defining the standards about how the test is done, right? We just what we are trying to do is capture a little bit of the information about what are the interface points for the test and provide that to the next level integrator so they can combine it together.
Yeah, and that piece sounds like it fits nicely with the JEP 30, whereas the other piece is more IEEE side.
Exactly.
Okay.
Exactly.
Okay. All right.
All right.
Yeah.
Okay, everyone. We'll talk next week then. Have a good one.
Yeah. Thank you.
Talk to you next week.
All right. Okay.
All right. Bye.
David,
Yeah.
hang on, guys. Hang on. One other thing. I just want to let you know what it is that we've been doing with the JEP 30-E document.
Okay.
Just like a 5-minute update. So one of the we have two companies now that has come to us saying that they want to put all their content into the part model format, and they've been doing it over the last 18 months. And each quarter they have discovered that, hey, we've got new complex units of measures that we haven't seen before, and it's arising from the introduction of multiple different functions onto the same device. So Infineon, for example, are putting in, making lots of components that are gravitational and pressure sensitive. So now they have complex units of measures that are a combination of voltage, watt, amps in relation to temperature or gravity. So what we've done is we've taken two approaches. Infineon are going through all of their parts, identifying all the different types of complex units of measures. We've done the same thing for the companies like IHS, supply frame, Z2 data, DigiKey, that type of information. We're looking at all the possible enumerated values of all the different types of units. And we're inserting those complex units as additional unit options inside in the JEP30, right? So that's one very big move.
Okay.
The second thing we're doing is Intel has come to us and said that when they're creating part models for to support a flow, and by the way, Intel has, yeah, okay, let's leave it at that. Right? They want to make sure that when I hand over the part model to another user, that that person properly understands the definition of a parameter. So we've got plenty of examples in where we see, for example, on a diode connection, somebody specifies VRM in the datasheet, where uppercase V, uppercase RM in a subscript mode. Well, that technically means reverse voltage maximum absolute value. But when we see that data represented in a data source like the information on a DigiKey website or in a Silicon Expert or an IHS or whoever, we have found multiple different representations of that, sometimes with just the VR, sometimes with lowercase v, sometimes with lowercase r,
Yeah.
sometimes with italics. When we check that against the JEDEC definitions for these different formats of the symbols, we just find that they have different meanings. Like, for example, a reverse voltage maximum at an instantaneous value due to a certain input current or a certain time cycle. So to address that problem, JEDEC has agreed that we will take all of the symbols that they have in all of their standards, and we will insert those into the IEC Common Data Dictionary, where we will expose that information via a third standards body called eClass to inside an API. Now, some component manufacturers are going to start taking each parameter in accordance with the ID that was assigned to it in that database and represent that on the datasheet, so that when I transfer that information from one system to another system, by connecting into the ID, you have the complete definition of that symbol, of that parameter, on the IEC website. So
Okay.
that's
So I see what you have done. That's still name based, right?
well, it'll be it's still name based, but it will be ID based by the time we have it all through the IEC process. So right now we're going through preparation of the data to hand over to IEC.
Yeah.
They have to then take it to their committee, but they already know about this. And so far, everybody is saying, right, this is a good way to go. It will help eliminate this interpretation of what the property and the symbol is.
Yeah, so the way I would have done it is probably similar but slightly different. One easy way is basically instead of using the name of a parameter to infer its meaning, the easy way would be to directly assign a meaning to a parameter. Let people define it whatever they want as a name, right? But if you have that dictionary of parameters and their meaning, all you have to do is add one tag that says type, right, parameter type equal to something, and then that something has to be part of the dictionary. Let people name it whatever they want to name it, right? Different parts of, right?
Yeah, as long as we tie it into a dictionary definition, we'll be fine.
Yeah. Yeah, you know,
So,
it's gonna be-
that's exactly how we're suggesting it, right? So
yeah,
this time round for June ballot process, we will just get all the units into the JEP 30, and we will get the first sample of the files over to IEC. For the next quarter, we aim to say, hopefully IEC will allow us to do this under the PASS agreement that we have with JEDIC. PASS agreement is publicly available specification. So we're trying to use that MO that we signed off with IEC to quickly release something through an IEC database. If that concept works, by the end of the year, we should have the content available on IEC. If that does not work, it'll take us 2 years to go through the cycle. So
yeah.
So that's the thing.
Yeah, it would
All
be
right.
good if we get the dictionary and just a reference to it, especially if they have APIs. That's awesome.
Oh, okay. But that's just a heads up on what it is that we're doing there.
Okay, awesome. Yes, thank you for that update, Michael.
Okay. All right. Thank you, guys.
All right. Thanks. Talk to you guys next week.
Thank you.
Thanks.